and I always struggle to fit enough, to have enough time to talk about all the different things that we have to do to Erlang to actually scale and allow us to do what we do. And the bottom line with FreeBSD is that we don't have to do much. You're going around the room, hearing everybody's comments about why they love FreeBSD. Those all resonate with us. And what I said was really true. With the size of the team we have, so there's a dozen of us on the server team. I don't think there's any other platform that we could have at that level, at the OS level, that would enable us to scale to the way we have with the staff that we have, because we don't really have to worry about what's going on with the OS, and we can focus all our time at higher levels. And so you'd think I'd learned my lesson about titling these things. Every time I title something that has a number in it or something like that, it means something different by the time I actually give the talk. If you happen to look at this year's Erlang Factory talk, you'll see what I mean about that one. But anyway, so we're past 600 million users now, unsuspecting, because so how many before coming today knew that WhatsApp used FreeBSD? Okay, most people. A lot more was made of the Erlang thing when the deal was announced than anything else. But so I've put together some topics to talk about. This isn't in any particular order. And if at the end of the talk you say, "Wow, what's the point he's trying to make?" Well, like I said, the underlying thing here is that FreeBSD has just been fantastic for us, and we haven't had to do much. We don't need much. It just works. And so I'll just give you some history of how it came to the company, some statistics that might be interesting, talk about a little bit about our architecture and some of the wins and challenges along the way. So I've been at WhatsApp for 3 years, or about 3.5 years. Like I said, we have a small team, so we all pretty much do a lot of everything. But I focus a lot on performance and scalability. Do a lot with our multimedia system, which we use to transfer pictures, audio files, video files between users on their phones. A little bit of security. We all do our own operations. We don't have a dedicated operations team. And like I said, we all sort of pitch in on everything. I spent 12 years at Yahoo before WhatsApp. I was on the platform engineering team there, and as you can see, my first exposure to FreeBSD was at Yahoo in '99 on 2.2.8, and I spent probably the first 5 or 6 years really doing a lot with the OS. I wrote a kernel module that we used there, and so I was kind of the point person in terms of doing the interface layer between the platform libraries and the OS. Before Yahoo, I was at Silicon Graphics, did some work on video serving there, and then before that, a couple other companies. So jumping right into sort of the history of FreeBSD at WhatsApp. So the decision to use FreeBSD obviously predates me. This goes back to the beginnings of the company with Jan and Brian. Both of them are old school Yahoo folks, so they both had a lot of experience with FreeBSD there, and how well it worked for a large scale global internet service. But I asked Jan a little bit about what specifically was going through his mind, starting a new venture, 10 or 15 years later, which would still make the decision to use FreeBSD at that point. And he was thinking in terms of, well, this is a messaging service. It's going to be a lot about networking. And the thing that stood out to him was just the quality and the performance of the TCP stack, how stable it was, and just being able to scale, knowing that the OS would scale with what he hoped would be a large-scale service. I don't know if at that time he thought it would be as successful as we are so quickly, but again, going back to the days of Yahoo, and knowing that this is an OS that you can count on. It's predictable. The releases are predictable. The documentation's great. And then just knowing the internals are going to be there when we need them. So here's a super crappy picture of our architecture that I stole from my other talk, because I'm just terrible at drawing pictures. Basically, we have our hundreds of millions of users on their smartphones out somewhere on the internet on the globe. We have two main front ends. There's the chat machines, which are our main connection point for the phones. Those are like I said, those are the primary connection point. That's where all the text messaging goes. That's where all sort of the metadata, as far as group memberships and profile pictures and all those kinds of things are transferred through. On the back end, we have a whole list of back-end services that are in separate clusters that keep our account data, keep our push tokens, group membership, profile pictures, as I mentioned, things of those nature. And then up there, the offline storage, it's not offline storage, it's storage for our offline stuff. But basically, we only keep data while it's in transit between a sender and a receiver. So if I send a message to somebody and they're not currently connected, then that message or that picture or whatever needs to be stored until their phone is connected. And so for the text portion, there we have those offline storage servers which capture that text while it's being stored before the other phones connect. The other major piece is the multimedia system, again, which is stores the pictures and the sound files and the video files while they're in transit. The protocols here, it's TCP in both cases. The chat connection is a proprietary encrypted protocol that we've optimized down as much as we can just to limit the amount of bandwidth and to increase the or lower the latency of the connection process, so people don't have to wait a long time to get their messages when they get a push notification. The MMS part is HTTPS. So a few numbers about where we are. Like I said, we're over 600 million monthly users now. At any given time, or we peak at about 140 million concurrent connections across the cluster. That sort of rises and falls. This number is actually about the same that it was back at the beginning of the year, last time I gave a talk on this. Even though our user count has gone up substantially, we play with the length of time that phones stay connected to the systems to optimize how often we think they'll be connected when they get a message, or to preserve battery life, or to improve latency. There's different factors there that make it more or less beneficial for the phone to stay connected shorter or longer period of time. So right now the phones are staying connected for a shorter period of time than they were at the beginning of the year, so we have a lower concurrent connection count as a percentage of the total users. So phones are connecting to us at a peak rate of about 440,000 connections a second. And we peak at about 1.1 million messages being sent by users to other recipients, and the outbound message count is going to be higher than that because of fan out for groups, but the inbound is about that. And we've just crossed a threshold where our users are sending over 1 billion pictures every day. And I spent a long time at Yahoo, which is obviously a large global internet service, but it's still hard for me to wrap my mind around the numbers that we deal with in terms of what goes on at WhatsApp. When I think about 1 billion pictures, I try to imagine what that, how many different pictures that is, or the 1 million messages per second. You can imagine 1 million messages, and then imagine that there's one of those 1 million chunks going every second somewhere around the globe. It's truly mind-blowing. So we have a fairly small cluster for the size of our user base, and I think, and I'll get into more detail here, but I mean, this is one of the places where I think that FreeBSD has really helped us to keep the size of our hardware footprint down. Obviously, from a cost perspective, it's important, but even more important, just sort of our operational complexity goes up as the size of our cluster goes up. And again, we're a small team, so to the extent that we can keep our server count down, that helps us keep things running smoothly with a small staff. So you can see that the front ends dominate the server count. We've got 200 of those chat front ends that do the text and most of the metadata, and then about 350 on the multimedia side. And that's the multimedia has really been growing rapidly ever since so there was an initial version that was available even when I joined, and we recognized that media would be an important part of the whole equation. So we rewrote that in 2012, and when we first launched that, we had about 16 of these servers. So you can see that obviously our user count's gone up substantially, but the demand for the multimedia stuff has gone up even more rapidly than that. So I pulled a couple graphs of just kind of our utilization across the cluster. So this is looking at one or maybe 2 or 3 servers of each type across the cluster. So the ones, and this is CPU utilization, so as a percentage, basically user plus system plus interrupt. And the ones at the top there are our chat front ends. So those are the ones that we run the hottest because those are predictable. We have a large number of them. We know how the load goes up and down based on what our user activity looks like. And as you can see, we would like to keep those closer to about 50% peak so that we have a lot of headroom for world events or things of that nature. So you can see that we're a little behind on capacity expansion right at this moment for those. A lot of the database-like nodes, those back-end systems, are the ones that are running down in the sort of the 15% range. And then, but some of them that take a lot more traffic, like our presence system, which keeps track of typing events, available, non-available, things of those nature. Those are getting a lot of events. So I mentioned that. So we do 1.1 million messages in a second at peak. The total number of messages being exchanged with the phones, when you include things like presence and last seen stuff like that, is probably closer to 3 million a second. So. So there's a lot of activity going on in the back end. One of the themes that I'll get to in a minute is the ability to use large RAM. So you can see we've got some systems that are using close to 400 gig per system across the cluster. So the bottom line on FreeBSD is that for us, performance has just been outstanding, so especially on SMP. So as I mentioned, it's important to us to keep our server count down, which means that we want to build really large servers. Obviously, we could, well, not obviously, but in theory, we could have built the same service with a much larger number of smaller servers, but there's aspects of the sort of the Erlang architecture that would make that more difficult. But the bottom line is, because we have had experienced such great scaling on the SMP side, it's allowed us to really just kind of scale and not have to worry too much about dealing with some of the other aspects of having a large node count. So the kernel has been, for most part, pretty free of contention. Once we did a little bit of tuning, the OS itself really doesn't get in the way. Erlang itself has been great. It has been a great choice for this particular application because of the sort of the actor model, where each phone can have its own lightweight process. And for those of you who aren't familiar with Erlang, so the programming model is you have lots of these little very lightweight processes. They can use, I think about 1,600 bytes of storage, and then just a very small control block. And so they're very easy. They're very quick to schedule. They're very quick to birth and die. And there's no for the most part, there's no shared state. So any sort of interaction in the system is all message passing. And the Erlang virtual machine, Beam, is very SMP aware. So it's very good at doing this message passing between all these procs in a way that minimizes the contention as much as possible. And so it allows us to put millions of connections on a node and not run into a lot of contention that limits the amount of scaling that we can do. For example, so last week I decided to just capture some graphs in terms of what happens when we really crank up the load on a server. So this is one of these front-end chat nodes. So I doubled the load on it, and you can see as the traffic ramps up, the CPU utilization starts out about 55% there or so, and kind of smoothly gets up there around 98, 99% and runs. And the remarkable thing is that, especially for these chat nodes, that we can run them all day at that level, and they work. Like, we don't typically, the way we monitor our systems, because this is a message passing system, when things stop working well, the primary indication is that process somewhere will stop draining its message queue as fast as it's being as things are being enqueued. So we're looking for backlog, basically. We're looking for backlog on a message queue on a process somewhere. And the remarkable thing about the way we've got the system tuned now and how it can scale on these boxes is that we can run them at this load, and you get little blips of 1,000 messages here or there, but the system will just keep running. And in fact, there was a time, I think it was last year, where we got a little behind. We weren't really watching capacity closely on the chat machines until one day we started getting thermal alarms on the nodes because they had been running at like 95% for 24 hours, and so the systems themselves, and then they were in one use at that point, and they had really small margin for cooling, and so we started overheating the boxes because they would just run and run and run successfully, and we didn't really know that they were running that hot. Here's the connection count. So it starts at about 625. And get it up to about 1.2 million. Now, back when we did our first round of optimization on this system back in 2011, we actually got these systems up to about 2.8 million connections. Since that time, we've added features. We've added encryption. We've added just kind of features into the protocol that make it a better user experience. And then our users have gotten a lot more active. So, whereas a user would send, I don't know what the actual numbers are, but, if there were 20 messages a day back then, there's 40 messages a day today. So per user, we're getting a lot more activity through the system. So the limits of what we can do on our current hardware are more in this range, whereas they used to be up closer to 3 million before. But again, you can see this follows the same shape as the CPU graph. And here's the actual work being done. So here's the packet rate, output packet rate. So you can see it gets a little choppy there at the top. It's not noticeable to the users because, again, this is an asynchronous thing. We're not doing real-time video on this particular application. But you can see that the graphs all match each other in terms of the scaling. One measure that we look at is the scheduler utilization. I'll talk a little bit, I'll talk about it now. So the way the Erlang virtual machine works is it's one big process with these schedulers, which are threads. And it's basically a scheduler on a scheduler. So each of these Erlang schedulers is going to have those lightweight processes scheduled on top of them. So the way that you can run it in different ways. The way we typically run it on these nodes is there's one scheduler per CPU thread. It's bound to that CPU thread, and then the Erlang process get scheduled on top of them. So scheduler utilization is basically a measure of how much the scheduler thinks it's running versus how much it's actually running. So if you had a lot of contention in the system, the scheduler would think it's running a lot, like 100%, but if you looked at the CPU utilization, it was only 50%. The rest of that 50% is time that the scheduler would like to run, but there's some sort of contention that's keeping it from running. The nice thing you can see here is that this graph basically follows the shape of the CPU graph until we get to the very top there. You can see the schedulers are at 100%, so they want to run all the time. CPU was actually running about 98, 99% of the time, but it's a pretty small delta there where there's time being lost because of some sort of contention either in Erlang or in the kernel. So this has probably been one of the biggest things that we have really benefited from, is being able to understand how these things would scale on these large boxes. These are some of the system stats while it's running at this level. So you can see, you know, the total utilization is in the 98, 99% range. That breaks out to about 80% user time, about 8% system time, 12% interrupt time, and there's just a teeny bit of idle there. And you can see the counts of the soft and hard interrupts, system calls, traps, context switches. So the hardware we run, so we're at SoftLayer, and we order bare metal hardware from them, which they rack and provision for us. We have a combination of 1U, 2U, 4U boxes, dual socket, Ivy Bridge, 2690B2, so we have a total of 40 CPU threads for each of these systems. A network attachment, there's SoftLayer gives us a front-end network which is public-facing and a back-end network which is private to our infrastructure. Each of those has 2 NICs, and we're primarily GigE, IGB NICs, and we run lag on both the front and the back. So we have 2 gig out the front, 2 gig out the back, and we have some boxes which are 10 gig IX NICs. Now I mentioned that we really load up on RAM. So our minimum RAM deployment is 64 gig, but we have some of the database boxes that are now running 768, which is close to the size of the disk. And we do that because of the type of database we run, which I'll speak about in a minute. For the most part, we use SSDs. The only place where we don't is on the video servers, where we need more storage than is economical on the current SSDs. So on most boxes, they'll just have one disk for holding the OS and doing the logging. But on the sort of the things where we need to store, and there'll only be either 1 or 2 disks on the database servers as well. On the things where we need lots of storage for, say, storing profile photos or the multimedia servers, offline storage, that's where we'll load them up with either 6 drives directly attached to the motherboard, or 12 drives attached by either Adaptec or LSI. But we run everything JBOD. We don't use any of the RAID on the controllers themselves. Our software platform, we're running various versions of FreeBSD 9. We use UFS everywhere. And I mentioned we don't use the RAID components, hardware components. On the video servers, we use gmirror on those 12 drives. So we end up with 6 mirrored drives to just give us a little more reliability on those. Really, our hardware problems stem from hard drive failures and RAM stick failures. That middle section, the SSDs, are super reliable for us. So it's one of those two things that we deal with on a hardware failure basis. We're starting to evaluate 10.1, but another thought that I had when we were in the circle was that almost every time in my past where I've been in a job and thinking about what the OS provides, I've always been thinking, well, always been looking to the next version, like, well, we need this, it'd be great if we could go to the next version. We need this, it'd be great if we could. This is like the first time, that we've been running on 9 for almost 2 years now, and that hasn't like entered into the equation. It's like, oh, I can't wait for 10 because we need X. It's just, it's been working so well for us that there hasn't really been a need to move forward yet. But we also like to stay kind of up to date with, the current development that's going on. So we are starting to look at 10. And Jan has the thing about 0.0 releases, so we always wait for 0.1 before we start looking at something. Rightfully so. So as I mentioned, we use Erlang. We're on R16, which is one level. So there are R17 is the current one, but we have a pretty extensive patch set that has addressed some of the contention issues that we found at the Erlang level. We run Erlang at real-time priority, and when I was writing this, I'm thinking that I'm not sure that we actually need to do that anymore. But this is something we started doing back in 2011 because the system was a little more brittle back then. So if there was some sort of perturbation that kind of kicked one of the Erlang VMs, so it couldn't run for a while, the system could get into a degenerate state pretty quickly. It's a lot more flexible now, so I'm not even sure that this is strictly necessary, but that's the way we run it in general. Like I said, our patches address specific issues we found off the shelf. Erlang has great support for FreeBSD. As I mentioned, it's very SMP aware. But even on top of that, I don't think it anticipates the kind of scale that we're at, where I don't think that it necessarily tested on as big a boxes, but certainly not as large a number of processes and large RAM and things of that nature. So those are the kind of things that we've identified. I mentioned the schedulers get bound to CPUs. Spent a lot of time in 2011 tuning the Erlang allocators so that the chunks that we'd end up with using gave us the best percentage of pages getting promoted to super pages. As you can imagine, that's fairly important when we have a box with half a terabyte or 768 gigs in it. We use Yaz, which is one of a handful of Erlang-based web servers. We can't use sendfile because of the way it kind of interacts with the Erlang runtime system. At the scale that we're at, we need to be able to schedule lots of I/O simultaneously across a small number of threads. So it's not the right model, but it works out for us even without that. We use Stud for SSL termination because the Erlang SSL implementation isn't super great. I mean, it works, but it doesn't scale to what we need. So we run Stud on the same box as the Erlang VM, and then we use loopback to proxy the connections back. For data storage, we extensively use Erlang's Amnesia database, which is a distributed NoSQL-like database. That's where we store like account data, group membership, those kinds of things. Amnesia works best, for us at least, when you keep everything in memory. So there's a big in-memory hash table, which is where all the database access is done. So all the reads, all the writes. And then Amnesia is basically periodically dumping those hash tables to disk, and it has a redo log that it's constantly writing for the persistence element. And then it supports replication to multiple nodes for increased availability of the data. So Amnesia is where you see the large RAM boxes is again, because we're keeping everything in RAM. For the large storage systems, for the offline mailboxes, for the media and whatnot, our storage is super simple, just flat files on a hash directory tree. As I mentioned, we use JBOD. We don't stripe for anything. There's basically one set of hashers on drive 1, drive 2, drive 3, drive 4, and we lay out the file system like we tune it per workload. So our offline mailboxes are this big, so block size is this big, frag size is this big, whereas the video servers are going to be a lot bigger, and the image servers are in between. This is a sample of metrics on one of the offline storage boxes. So you're seeing one drive here. So on one drive, kind of running at peak, it's doing 9,000 writes a second to one of the drives. So multiply that by 6 for that machine, and multiply that by 32 to get the total write rate for all the offline messages. What we found, and Kirk helped us with this a while back, trying to figure out, like, is there anything more that we can get out of these boxes? But what we found is, because we're doing this 24 hours a day, that with the drives we're using, basically once we got to about 45 to 50 megs of write per second, that's all that the drives could do. So they could do that all day long, but they can't do any more than that at that constant rate at the size that we're doing. And you see the reads is pretty low. So most of the offline storage is pretty transient. Like I said, it's only during the time between somebody sends a message, we send a push notification, that phone wakes up, connects, grabs the message. So half of the messages get delivered in the first, I think, 25 seconds. So for the most part, a lot of the writing we're doing is just for persistence, and it never actually ends up coming back off the disk because it's delivered long before it gets flushed out of either the application level. We have an application level cache, and then there's the caching in the OS itself. In terms of, going back to some more history, so we were on 7 in 2009, 2010, and worked well. There were a few bugs, but our scale was smaller at that point, so it was easier to deal with. FreeBSD 8 is when I came on board, and it was better. One of the first things I had to look at was, so one of the features of Erlang is that this message passing is transparent across a cluster. So if I have a PID handle, I can send a message to a process, and it gets delivered to the process wherever it is on this node, on a different node on the same server, on a different node on a different server. And that all gets routed over this distribution network, which is this big mesh of TCP connections between all the nodes. And so the problem they were having when I showed up was occasionally these disconnections would disconnect because they'd get a message and they'd try to deserialize it and it'd be junk. And long story short, it turned out that the message was being corrupted between the time it was written to the socket and it was going out the NIC. And so when we turned off zero copy sockets, that solved that problem, and we never looked back. So a lot of these things we sort of solve and then move on and don't worry about coming back to. We had a few problems with, I think, NIC lockups or something with IGB, and I don't remember back, but I think I backported the FreeBSD 9 version or something like that, and it took care of that. And then we were also looking in terms of, when we were tuning the system, on our particular hardware, the kernel was refusing to use the TSC for the time source, so there was a little patch in there to force it to do that because the TSC was stable. It just, for whatever reason, it wasn't being detected as so. And I mentioned that we got to about almost 3 million connections per server in those days. We started on to 9 in 2013, and it's, like I said, we haven't been looking for the next version because it's been really great. Very, very rare panics. I can't remember what the last one was. I mean, we do get panics, but they're almost always either uncorrectable machine check or it's a panic in UFS because of a previous crash that corrupted the file system. But as far as just random things out of nowhere that we don't know about, almost never. We've worked on a couple enhancements. So in these systems that have these big hash directory trees, we'd like to be able to cache the whole working set for the directory. And so that exceeds 2 gigs in some cases. So we've cranked up the dir hash size, and then been playing a little bit with increasing the max TCP retransmit interval so that we can survive. So a lot of most of our outage time this year has been due to losses, problems with the back-end network. And those outages last between 30 and 90 seconds. And when they go out to about 90 seconds, some of those disconnections disconnect because of the caps on the retransmit interval. So we've been playing with bumping those up a little bit just to try to get us past that 90-second barrier, which will allow us to stay connected longer, which is what we'd like. How am I doing my time? What time do you want me to? You want me to keep rolling, or?
You're good. You can take questions or keep rolling.
Okay. I'll just run through this tuning stuff real quick. So we don't do much in terms of the kernel config. We just it's kind of a yawn OCD thing. We take out everything that we don't need and put in the debugging and tracing stuff. Just a few tunables in the loader conf. One thing that we discovered not too long ago was that the auto tune for the buffer cache on our large memory systems was allocating like 12 or 18 gig or something for the buffer cache, which was ridiculously larger than we needed. And it was all this wired memory that we were able to get back by just forcing the count down. Then we obviously crank up the number of files per proc and processes, and then widen out the TCP hash tables pretty wide. And then we also try to crank down the host cache to basically disable it as much as we can, because at 40, each of these servers is getting 3,500 to 4,000 connections a second. So it's never going to see a connection that it knows that the connections when they come back are long gone out of the cache. So it's just time spent for no reason. We crank up capacity on MBUFs and sockets, but we don't run into issues there. It just works. I mentioned that we patched it so that we can have a larger dir hash for UFS. We played a little bit, so going back to this offline storage, so I spent a lot of time sort of the end of 2011 trying to figure out how can we lower the write rates on those SSDs for the offline storage. And we knew that somebody will come and fetch that mailbox pretty shortly after it's written. So ideally, we'd be able to just kind of have that. We write it into the file scripter, and it would just kind of hang around until for the next 20, 30 seconds. And if they came along and read it, great, and we can delete it. It never goes to disk. The problem we have is, I remember struggling with this at Yahoo too, with the user database. As we cranked up the dirty buffer limits and tried to lengthen out the sync delays, the syncer just gets really bursty. So it'll be a long period of time where there's nothing going to the drive, and then boom, it's just completely saturating the drive, and then it would go back to not doing much at all. So the overall performance ended up being less because there was this period of time where it wasn't driving the drives at all. So we ended up just going back to the defaults, which basically means everything we write to the file descriptor ends up getting written to the drive, and then just using that application layer cache to take care of the read problem. So issues. I mentioned that we deal with panics in the case of filing system inconsistencies, but we just kind of deal with it basically after a crash when the system comes back up. And this is because soft updates doesn't save us from write caching on the drives, which we need to get the performance. So after coming back up after our first crash, we let FSCK do its quickie soft updates thing, and then we just start running. And hopefully we're okay. Hopefully there's nothing wrong with the file system. If we crash again, the second time we come up, then we do a full FSCK in parallel on all the drives. And I don't think this has happened recently, but it used to be the case that sometimes when we'd run the parallel FSCK, it would panic again. So our third time we came up, we'd run them sequentially, which for some of these could take hours, which is why we sort of shortcut it, try to do the minimum that we can to keep the system running. I mentioned the bursty syncer behavior. I also mentioned that the Erlang VM is one big process with all these threads in it. Well, it's not actually not that many threads. I mean, there's one scheduler thread per CPU thread, and then we typically run with 29 async threads, which happens to be the magic number for best performance. So there's actually not that many threads, but on these systems where we're doing lots of reads and writes from files, there's one file descriptor table, and we get a lot of contention there. So we have to make sure on those applications that we open and close files as little as possible. So we'll open the file, we'll stat it, we'll read it, we'll trunk it, we'll write it, we'll do whatever we do before we close it, rather than trying to open or close it multiple times for that case. We've only just started looking at PCB table contention problems because we're trying to scale up a server that has that stud-terminated SSL on it, which means that for every socket coming in, there's another 2 sockets on that loopback between the proxy and the application. So if we're trying to support 1.5 million coming in, that ends up blowing up to 4.5 million sockets. And so we've run into problems with with the interrupt handlers competing with the net ISRs, which I guess are doing some of the loopback traffic with the application itself, and there's some degenerate problems there that where the system kind of tips over that we've been trying to figure out. But that's really it. And like I said, and this last one could just be solved by not being so aggressive on how many connections we're trying to put on these boxes. That's not interesting. So our wish list isn't big. I think being a mobile app, I think multipath TCP will be interesting for us for 2 reasons. I think it'll probably become more and more interesting on the smartphone platforms and give us better capability to stay connected to the phones as they're managing their multiple wireless connections. It's also interesting to us on in the server cluster itself, because as I mentioned, we're dual connected on there's a front-end network, a back-end network, but the machines can talk to each other on either of them. And it would be nice if we could actually run those distribution channels over both networks and have that reliability through the fact that we actually can use both networks simultaneously. We've been trying to do that at sort of the application level. We've been trying to do it at the routing level. Haven't been successful doing that, but that's one case where that might help us out. And then faster large RAM boot. Some of these boxes, when we boot them, even if we're watching the console, they'll sit there and sit there and sit there, and there's no progress bar, so we don't know how far along they are. But that's kind of a I want a pony kind of thing.
Loader.com tunable is disabled attach.
Yeah. Oh, really?
Yeah.
All right, we'll take a look at that. Like I mentioned, it's probably something we can disable because we never find the errors when it's booting. We only find the errors when it's running, and it craps out. But anyway, hopefully that was interesting. I'll take questions for whatever time I have. Yeah.
How do you deal with XMPP presence and multiple endpoints? Do you just deliver the same message to all endpoints, or do you?
So currently we only support one endpoint. So your phone is source of truth. So that's your presence. Yeah?
Do you actually do encryption on those chat boxes, or you have some SSL terminators?
So the encryption on the chat boxes is done on the chat boxes. It's a proprietary. I mean, it's AES, but I mean it's our own. We optimize. Originally, we started with SSL. But we wanted to eliminate as many round trips as we could, and because of the fact that we had control of both ends of the connection, we went for something more optimized. But it's done on those chat systems. Yeah.
What are you using for configuration management of the clusters?
Configuration management of the clusters. Make. We don't have that many types of servers, and despite the fact that we have a gigantic user count. We still don't have a very big node count per engineer, and a lot of these are identical, and so we haven't found the need to automate that yet. So it's actually just making manual operations at this point. Yeah.
Maybe a question you don't want to answer, but how much do you have to deal with national security letter, lawful intercept kind of stuff?
I can't. Well, I can't answer that both because if I knew the answer, I couldn't answer it probably, or they wouldn't want me to answer it. But I don't know the answer. I'm a technical guy. I don't deal with the policy stuff. So.
Someone else's problem is the direct answer.
Yeah, exactly.
So all the Erlang patches, have you open sourced it or it's available publicly?
I'm sorry, which?
The Erlang patch.
Yeah. There, it's on my Git repo basically. Redar. Anything else? Yeah.
Have you guys tried selling some of these solutions to Facebook?
Yes, in fact, they bought them. Yeah.
So for testing, do you try to engage 1% of your users to, for example, test new improvements, or do you have some kind of a test farm where you can actually simulate some notion of the traffic you have on the production box?
We do a little bit of, so the question is how do we test new features and so on. We do a little bit of A/B testing, but it's not very, we don't have a big framework for doing that. Mostly we just kind of go live with stuff. We've got a lot of, and we won't necessarily, if it's a major change, we won't push it everywhere. We'll put it on, if we have an optimization on something, we'll throw it onto one chat server and see what happens, and that's only taking 0.5% of the traffic. And it's easy to kill it and shift that traffic if it causes a problem. The problem is, so when I first started, we had like a whole test harness. It died. I'll just hold it. Hang on. Hello? Hello?
Move to a different location.
Testing. Here you go.
Hello? All right, I'll use this. Hello. Okay, that works better. The cone of silence. Hello?
Speak up.
I'll just talk loud. What was the question? Testing. So when I started, we had sort of a test harness where we'd throw, we'd spin up a bunch of AWS instances and throw traffic at the site. And, even back in 2011, we quickly outgrew the ability to throw enough traffic at the system to test it the way we need to do it. So on some of these systems, we'll do kind of T-testing, where we'll send, especially on, say, offline. I spent a lot of time optimizing offline, because it was a big pain point. Back in those days, we'd have, outages every once in a while, and when the big pain point was, these messages get queued up, and then when we let traffic back into the system, it would just destroy the offline system because there's this flood of messages coming in. So it finally occurred that we were never going to be able to test it and give it the right traffic mix in a sort of synthetic way. So really we moved to a model of either testing it live or testing it in parallel with testing it in parallel with sort of T-testing. So especially for offline, when we throw things to the production offline servers, we throw them to some test servers, and then we could really play around with it. So that's primarily the way we do it these days, just because it's so hard to simulate, the mix of 1 million messages and how many of those are media, and how quickly are the presence transitions, and just all the different intricacies of what actually causes load on the system. Yeah.
You mentioned network problems. Were the problems on the system or switching layer?
The network problems were not in the network infrastructure. So upstream of all the servers. Aside from those occasional IGB problems we had back in 2011, the network's been totally not an issue for us. Yeah, in the back.
Can you talk a little bit about the tools you use to do performance analysis of the cluster, and are there things in that area that make your job easier?
So the question is, what kind of performance tools do we use? So last time, so I did a lot of that back in 2011, and there was a certain amount that we did at the OS level, primarily through PMC was a big one, and then inside Erlang, there's too many different ways to profile Erlang, so we end up using fprof in there. You know, a lot of times the problems that we're running into actually show up in top, you know, in the wait channel when we get these things really loaded up and we're trying to figure out what the problem is. It's a pretty, like for instance, the file descriptor table thing. It was pretty obvious when on those particular machines, on those particular machines, what the problem was, because you'd see a bunch of things get stopped in that particular piece of code, and there aren't many places it locks. Yeah.
Have you looked at using the polling feature to reduce interrupts from the network card?
I'm trying to remember.
To save that 10% of people who really can launch interrupt?
I think we did experiment with that, but it wasn't conclusive. So, but it's worth revisiting for sure. Yeah.
What methods do you use to spread the connection or load across the infrastructure? Like
we DNS. So the load gets distributed by DNS basically. So we have 13 machines in each of 16 different DNS names, and they just get rotated by the resolvers. MMS, we actually load balance internally because we know when somebody's going to send, we can assign them to a machine. Okay, one more? Yeah.
So was Erlang your secret sauce right away after you started, or was it something that you guys migrated to once you reached certain copies?
Well, no. So they started with Erlang from the beginning, and that was before my time. Primarily because it was they wanted an open source XMPP server, and it turned out that the Erlang one made sense. Now, and I think there was some thought to, well, this is this is kind of a telephony project system, right? We're trying to replace SMS, so this Erlang thing from the telecom world seems like a good fit. And I think by the time I got there, it was, it didn't take me very long to, even though it was a strange thing that I was actually like, people wanted to use it at Yahoo, and I was kind of like, we don't need yet another language. But it didn't take very long for me once I got to WhatsApp to realize that was really, really powerful. And one of the things I haven't mentioned about it that works well for us is basically being able to do nonstop, do hot code loading is a huge win for us, because our systems have been completely down only once in the last 3 years, which is right after the Facebook announcement. But but every other, we can upgrade these systems while they're running with millions of people on them, running at full speed, and it just makes our lives so much easier. And then with that, I think I've burned up enough time.
All right, thanks a lot.
All right, thank you.